start, live streaming starts. So what we are going to start today is the last part of the theoretical arguments for the class. So we will discuss what we may call biological processes. And in doing this, we shall start by introducing the processes of light extinction, but is strictly connected with the process of photosynthesis, because as you know, photosynthesis depends on the presence of light. So we shall now introduce a way of modeling the effect of extinction of light due to terrestrial obstacles. And then we will go into some details on the photosynthesis process, and then we will briefly introduce algal growth, but in actually algal growth, we will go in much more details for the next lectures and lectures of next week. So let's start by light extinction. As we already know, light is the main energy source for ecosystems on the surface of the planet, and there's a key role in ecological processes like photosynthesis, transpiration, evapotranspiration, but also in energy transfer and climate regulation and so on. Hence, the quantification of the energy reaching the Earth's surface from the sun, and so the living organism, is very important. This is why we shall introduce today a model that helps in evaluating the quantity of light that reaches the planet, in particular reaches the photosynthetic machinery on the surface of the planet from the sun. So classically, we model light extinction by employing a very classical model that is the Lambert-Beer or Borger's law. It is really by large the most famous model. If we call a capital E intensity or irradiance, that is measured in watts per square meters, so this is an energy flow per unit time, an energy flow density per unit time, surface density per unit time. We may write that the variation in time of intensity of light is equal to a constant k minus a constant k times the intensity of light itself multiplied by the distance traveled by this light. For example, we may observe some experimental data in which, for example, we link photosynthetic active radiation. I recall it is the 56% of the light arriving on the surface of the planet with the depth at which we are measuring this quantity. And in particular, we observe an exponential decreasing model in which the irradiant, the photosynthetic active radiation part decreases exponentially with the depth of the water body. What we are doing here, we are measuring the quantity of light that crosses the water body, and we're measuring how this light diminishes with the depth crossed by the water body. The model is a classical first order dynamic model, first order cinetic model, in which we write that the intensity of light at depth z is equal to intensity of light on the surface of the body, of the water body, multiplied by an exponential decreasing factor e power minus kz. But I recall you, photosynthetic active radiation is the 52% of all the light arriving on the planet surface. So this is why we are multiplying with 0.52. There should be an error here. I don't understand. This is 0.52 multiplied by intensity of radiation exponential decreasing factor. So in the hypothesis of an homogeneous media, we may, of course, find a solution of this differential equation, first order differential equation, and the solution is the classical decreasing exponential function. Of course, we model work well for low concentration media. It means media, water bodies with not too high suspended solid or particle densities, and K, so the constant of light extinction, depends on the medium, on the direction, on the wavelength, and so on, depends on several factors that are related to the characteristic of the water body we are looking at. So we said the classical law employed for modeling light extinction process will number be a law is this one. So the intensity of light that reaches depth Z of my water body is equal to intensity of light that arrives on the surface of a water body multiplied by this exponential decreasing factor, but takes into account what there is light absorption or extinction as light travels through the water body. The ratio intensity of light out divided by intensity of light in, so reaching the surface of a planet, is called transmittance. And we may have several applications of this model, for example, in spectrophotometers. The model employed or embedded into spectrophotometers, it is a decreasing exponential Lambert-Beer model. K times Z is called the optical depth, and it is a measure of the ability of a layer to block light. In the cases of heterogeneous medium, we may apply this relationship separately to different layers by simply varying the factor K with K parameters. So it is a distributed model approach, distributed parameters model approach, in which we may change the value of the constant K or parameter K according to different points of the water body. This is what we may say about light extinction in water. What about light extinction in the atmosphere? We shall recognize that not all solar radiation approaching Earth's surface actually reaches the ground, but because there is a more or less extended absorption of light during the atmosphere. So extinction is caused by two sub-physical processes, but scattering and absorption. Scattering is refers to the fact that photons are deviated by gases, for example, aerosols, and there is no energy loss during the diffusion process. There are two types of scattering that are classically employed for describing this effect, which is the Rayleigh scattering, which particles, we consider particles which have a diameter that is 1/10 of a wavelength. This is typical, for example, for atmospheric nitrogen or for oxygen for visible radiation. So for visible radiation and particles with dimension of atmospheric nitrogen or oxygen, they are subject to a Rayleigh scattering. The other form of scattering is the Mces scattering, that refers to larger particles, so particles which with a diameter that is up to 10 times the wavelength of the incident radiation. The other process, the process of absorption, refers to the fact that photons hit atmospheric gases like oxygen or ozone or atmospheric or gaseous nitrogen or water vapor or CO2 and so on, and then this light is also absorbed by aerosols, but may be of natural or anthropogenic origin. Then the energy in this case is transformed into the heat of radiated irradiated energy. So in these cases, we may employ these two models for describing extinction of light. The two models refer to Rayleigh extinction for short wavelengths and to Mie extinction. So to Rayleigh scattering for short wavelength and to Mie scattering for larger wavelengths. We may rewrite the Lambert-Beer model, this way. So we have battery energy that exits from the system, and we are talking of the atmosphere here, but of course it is as well applicable for water bodies. I recall you that the difference is essentially in the way we evaluate constant parameter k. In this case, we may say that we may introduce the definition of the optical air mass as the inverse of the cosines of latitude, so of incident angle of sunlight. Phi is the incident angle, but by it refers, it is similar or proxy of the latitude. For example, in at the zenith, this angle is 0. So if vertical radiation, the angle is 0. In this case, we may express k, light extinction coefficient, as a contribution of several factors. For example, a quota due to scattering by gases. A quota is due to scattering by aerosols, when we may include also extinction due to absorption processes, both from gases and aerosols. In inhabited regions, usually K is due to suspended particles is much larger than the K due to gases. This means that inhabited regions, in which there is anthropogenic activities, that, as you know, produces particles and wastes that are emitted into the atmosphere, the extinction effect is largely extinction effect due to the suspended particle is largely more important than the extinction effect due to the atmospheric gases. We say this by saying that the K of suspended particles is in general larger than the K due to K absorption coefficient due to gases. We have empirical relationships for latitude larger than the 60 degrees. So we are talking about polar circular polar latitudes. In this case, refraction is depends on is non-uniform and depends on temperature, depends on the presence of clouds and other substances, and it is linked also to the Earth's curvature and to air density that is strictly linked to temperature. So this is what we may say for light extinction in the atmosphere in general. Now let's go into some more details. How can we make this model more precise? For example, let's focus on water's ecosystem. We may recognize that too few, or in some conditions even too much, light can limit primary production. And as you know, our focus is in primary production, meaning on phytoplankton growth or macroalgae that are primary producers. So we recognize that there is an optimum amount of light, not too much and not too few light is necessary in order to a process to perform with an optimal efficiency. Scattering and absorption due to water and suspended and dissolved substances in water. So there is, of course, a linkage between the absorption of light, the light extinction that is due to scattering and absorption, and the quantity of suspended particles or dissolved substances in the water column. Also, there is an our way round effect in which primary producers can influence extinction. This is called the phytoplankton shedding and the self-shading effect, So this is a feedback in which, for example, primary production may have a significant influence on light extinction by stopping light from crossing water layers due to the fact that there is algae increasing concentrations what may stop light from crossing the layer. In general, we consider that light used in photosynthesis is mainly in the visible range. So we have said this is between 400 and 700 nanometers. And photosynthetic active radiation is measured as an energy density flow, watt per square meters, and may be also measured in terms of photosynthetic flux density, PPDF, that is the number of incident photons in the visible range per unit time, per unit area. I recall you that this is a definition that calls to play the Einstein, that is moles of photons in the visible range, for example. In this case, we may find a relationship between the photosynthetic activity and the photosynthetic photon flux density in terms of number of incident photons in the visible range, that is the energy range or wavelength range for which photosynthetic activity is present. Then we have another definition, that is the definition of the euphotic or photic zone. In this case, we may define the euphotic zone with a part of a water body in which we have, for example, that the respiration due to primary production is exactly equal to photosynthetic, the energy produced by photosynthetic activity. You know that we can switch easily between energy and energy flows because we know that different types of biomasses have different contents of energy according to the characteristics of a biomass itself. Then we may define the euphotic zone, this part of a water body up to which we have 1% of photosynthetic active radiation. So this is the zone in which the photosynthesis takes place in any case. So we have a zone in which we have at least 1% of par or more than that. When this zone in water body extends from few centimeters under the water surface to even hundreds of meters in particular conditions in which we do not have too much suspended solids. So, as we said, we employ the Lambermere model, that is an exponential first order cinetic exponential decreasing model. We said that we make all the, we hinder all the complexities or particular characteristics of a water body in the K constant. K depends, of course, on the wavelength and can be determined using photometers, for example, at several depths. In particular, we start by assuming that 56% of the radiation arriving onto the surface of the water body. So this E in is the 56% of radiation arriving into a water body. Is the starting point, and then we have a reduction that is dependent on the depth of the water body. After a few meters, we know that light becomes monochromatic green, so the photosynthetic activity decreases dramatically. We can complicate this model in various ways. For example, K can be computed in several ways. We may, for example, include the dependence of K to the K in water due to dissolved materials or K in water due to particular suspended particles. In this case, we may find a relationship between the K due to suspended particles and the concentration of the suspended particles in the water body. So this is a way of expliciting the dependence of K on the concentration of the suspended particles. When phytoplankton, for example, has the biggest influence in light extinction, and we are talking here about the self-shading effect of phytoplankton, but is happens typically in eutrophic lakes, shading or self-shading. In this case, we may express K with a more explicit model, for example, by including a dependence on the concentration of algae. So this is the first linear dependence of the concentration of algae of a light extinction coefficient, or we may have a nonlinear dependence on the concentration of algae. And for example, in oligotrophic ecosystem, B, that is background turbidity, is what dominates light extinction. So in this case, we make K dependent on a background turbidity due to suspended materials and a feedback effect due to the fact that there is primary production, so algae that are growing and in this way are stopping light from crossing the different layers. Again, our way of making it explicitly more sophisticated is the light extinction model, is that of writing the constant of light extinction K as dependent of, for example, on two parameters A, B, and concentration of algae, or for example, concentration of total suspended solid. And there are several ways of modeling this total suspended solid concentration, but may be made dependent on the concentration of algae linearly, or the concentration of algae non-linearly, or simply the concentration of total suspended solid. So this is the first way. So this model may be B times total suspended solids, or maybe K0 plus A1 plus A2 times the concentration of algae, and so on. In general, we know that the light extinction coefficient may be made directly dependent on a measure that is called the Secchi disk measure, SD, you know very well. The Secchi disk measure, you take a white disk and you make it go down deeper and deeper, and you measure when you don't see anymore the Secchi disk. So this is a measure of water turbidity, classical measure employed by engineers measuring water turbidity. So in this way, we may make the constant of light extinction K dependent on the Secchi disk depth. And this is another way of explicitating the model and finding a way of calibrating the model. So typically, what is the role of K? I recall you with transmittance is equal to what? To the E out divided by E in. So what arrives on the surface of a water body and what arrives on depth Z of the water body. In this case, we may write that the transmittance as a function of the depth tends to decrease, and it decreases more quickly as the depth of the water body increases. So on the surface, we have top transmittance, and when we go deep, we have a decreasing, significant decrease in transmittance going to zero when there is no more light crossing the water layer. In particular, we may observe some experimental measurements of light extinction. In this case, we have plotted photosynthetic active radiation as a function of the depth of the water body. We see that, for example, for the same water body, we have different measures in January or in February. For example, this is a turning point at our latitudes in which January we have the first bloom of primary production between January and February. So what you see is that the photosynthetic active radiation depends more and more dependent on the depth as the algal bloom proceeds. So the blue dots are experimental data, and we may interpolate these experimental data by employing the classical number pair exponential decreasing model. And there are several ways of making this interpolation depending on how we model the dependence of a light extinction coefficient K. So for example, the green line represents a Secchi disk dependence of a light extinction coefficient, while for example, the dotted line represent a model that explicitly links the light extinction coefficient to the density of to the density of algae, whose chlorophyll A is a proxy, and to a quantity of total suspended solid into the body. Of course, this last way of modeling the effect of light extinction is gives worse results because it includes a lot of complication and variation to the systems, but it has the advantage of being predictive. So you have a model in which you may, for example, link the primary production as a function of the total suspended solids. Or you may link, for example, the Secchi disk depth measure to the light extinction effect. This more or less is all we have to say concerning water ecosystems, but we know that we would like also to be able to measure the effect of light extinction also in terrestrial ecosystems. In this case, we must realize that the canopy of the trees can attenuate the light, relevant effect in tropical forest. Then this effect may have strong influences on the underlying vegetation or on the undergrowth or on the animals thriving on the land, or may have important influence over nutrient cycling effects, of course. Also, agricultural crop spacing, water balance for irrigation are all our parameters that may be influenced by light extinction processes. In this case, we have to introduce a further variable that we may call the surface of a canopy that may stop light. We observe that light arriving onto the leaves of the plants are partially reflected, partially retransmitted through the leaf, and partially absorbed. And this, when it is absorbed, this light is the light that performs or drives primary production. This is, of course, a complex multi-scale problem for which we have very few general models. In general, the most applied model is the so-called leaf area index model, in which we model the effect of vegetation by introducing a new parameter we may call, or a new state variable we may call leaf area index. And we say that the intensity of light reaching a certain depth in the canopy of terrestrial vegetation is equal to what arrives on the surface or the top of the canopy multiplied by an exponential decreasing factor, that depends on light extinction coefficient K, multiplied by the leaf area index parameter that describes the quantity of surface that may intersect or stop light from crossing. Of course, leaf area index depends on the Z, so on the depth of a canopy, on the depth of a system that we're saying, what we're studying. For example, we may have a lower leaf area index when the vegetation is less dense. So in the case in which the canopies or the leaves of the trees are less dense, you will have a larger leaf area index when you have a more dense vegetation. So leaf area index at depth Z is the accumulated leaf area index from the top of the canopy to depth Z. Leaf area index is the ratio of the total one-sided green leaf surface to the surface of the ground underneath the canopy, or the projected needle area per unit of ground surface. So by this parameter, we are able to model somehow the effect of vegetation covering on extinguishing extending light. As it is customary, we model says that the quantity of radiation, intensity of radiation depth Z dependent on the leaf area index, and this dependence is made by calculating the quantity of energy coming from the sun on the surface of the canopy. So these may be measured by the incoming photosynthetic photon density flows on the top of the canopy. I recall you this is an Einstein measure of energy, and I recall you that the Einstein measure depends on the particular wavelength of the photons you consider. In particular, for photosynthesis, we consider photons in the light range. K is connected to the average leaf orientation to three species. So K is describing a characteristic of the trees that are present onto our ecosystem. Often the hypotheses of a Lambert-Beer model in this case are not realistic. I recall you that these hypotheses are that of homogeneous and isotropic media. This is not always possible. There are, of course, other models that are more complex, complicated, even complex 3D vegetation models, or field measurements by hemispherical photography may be employed. But in this case, the situation is much more complex, so the type of model you are going to use will be much more complicated. This is why we shall always focus on water bodies, in which the situation is much more easy to model, because water bodies tend to be more homogeneous and tend to be isotropically related to light rays. This light that reaches the canopies or the trees on the terrestrial ecosystems or the water bodies on water ecosystems is this energy is the energy responsible for the process of photosynthesis. I am resuming here a very general chemical equation describing photosynthesis, in which we have certain amount of carbon dioxide, CO2, but combines with some water that employs photons energy to produce what? Glucose, C6H12O6, that is a prototypical molecule of glucose, plus some oxygen. In general, we have a process that converts carbon dioxide into oxygen, leaving as a product carbohydrates or sugars, if you want, and oxygen gases. And this is mediated or is fostered by the presence of photosynthetic active radiation, so light in the visible spectra, energy, solar radiation in the visible spectra. What are the limiting factors? We employ some empirical model in order to evaluate what are the limiting factors of the photosynthetic process. So we may write that the photosynthetic production is equal to a constant K multiplied by a function that describes the effect, the limiting effect of the various parameters, for example, max demand for limiting factors. I recall you that these limiting factors typically limiting function typically are in the range 0, 1, meaning that 1 you have the most limit, 0 meaning when this function is 0 you have the most limiting effect, while when this function uh, value is 1 you have the least limiting effect. Of course, there is a light effect that is linked to an optimum irradiance. So energy is needed, but not too much energy, as we said. In this case, chlorophyll absorbance spectrum in the range 400, 700, 9 nanometers, and depending on species of bacteria that are typically bacteria chlorophylls, but may also work on longer wavelengths of the Dewey. So we have limitation due to limiting effect due to light, a limiting effect due to the presence of inorganic carbon type, typically carbon dioxide, and a limiting effect due to the presence of water, because this process is, of course, performs well or optimally in water conditions, in water ecosystem. There is an optimum effect due to temperature, as we will see soon. Temperature has a relevant effect on the proceeding of all biological processes. And then there are other plant characteristics and state, for example, leaf area index or reproductive states of the presence of nutrients, like, for example, nitrogen in chlorophyll, and so on. These are all limiting factors. In general, we may say that the process of photosynthesis may be described by this type of models. We classically subdivide the photosynthetic machinery into two classes. The light acclimated photosynthetic machinery, so these are machinery that are most producing in high light condition, strong light condition, or there are shade acclimated photosynthetic machineries for which the saturation value of a net photosynthesis value is lower. This means that this machinery, the shade acclimated machinery, are able to perform photosynthesis even in condition of low light irradiation. So we may write this model by plotting net photosynthesis. Net photosynthesis is the quantity of energy produced by the photosynthetic activities, but it's measured in terms of energy content of the biomass produced, minus the energy employed for respiration by the photosynthetic machinery. So we have that photosynthesis at saturation level depends on the species of algae, the species of plant, but also on our ecosystem characteristics, like, for example, the temperature or pH and so on. So we may plot the net photosynthesis effect, what is energy produced by photosynthesis minus energy employed for respiration by the photosynthesizers, is a function of irradiance, and we see that at growing irradiance, so more the light, the process is a saturation-like process, for which we go to a saturation value of a net photosynthesis, for which, for example, in case of shade acclimated photosynthetic machinery, we have lower value of the saturation of a photosynthetic net photosynthesis ratio, or we may have for these machineries that are light acclimated a higher value of saturation quantity of net photosynthesis. Of course, we know that there is not only chlorophyll photosynthesis, but there are some autotroph bacteria with bacteria chlorophyll pigments, for which, for example, they may employ other elements as electron donors. In this case, we will try to synthesize different biochemical process, that is photosynthesis, photosynthesis with sulfurs, acids, sulfur or in sulfuric condition. In this case, as well, you have but CO2 and the energy in with acids are transformed. CO2 using the energy contained into these acids are transformed into chlorophyll, sorry, into carbohydrates plus some sulfurs plus water. In this case, the electron donor, that is the hydrogen sulfide, so this acid, instead of water, the reaction takes place only without oxygen. So this is a reaction that happens in an oxic condition, and there is no oxygen production in this case. Instead, there is a production of sulfur. This is what typically happens when you find these environments or ecosystem which you can smell this egg, rotten egg smell. There are also some cyanobacteria or chlorophyll that can perform this reaction. And these are bacteria that are opportunistic, meaning that they can change the way they perform photosynthesis according to environmental conditions. The photosynthesis produced by chlorophyll are typically produced by a classes of organisms called cyanobacteria or blue-green algae or cyanophyta and so on. These are unicellular prokaryote bacteria that can form colonies and they can reduce nitrogen, for example, fix gaseous nitrogen into ammonia. This is often performed by symbionts. They can reduce sulfur only in some conditions, but they also can reduce carbon, with typical classical chlorophyll photosynthesis processes. In this case, atmospheric oxygen is a limiting factor for cyanobacteria, in which the photosynthesis is performed into the cytoplasm, but not in specialized organs, because these are prokaryotes. I recall you that prokaryotes, bacteria do not have specialized organisms. Chloroplasts probably are derived from cyanobacteria but are embedded as endosymbionts. So in this case, we may recognize as Lynn Margulis, recognized in the late 70s, 80s, early 80s, but some steps of evolution were performed by symbiosis of different machineries that were able to perform different biotechnologies, and they stuck together in symbionts. What is the relationship between photosynthesis, respiration versus net photosynthesis? In chlorophyll photosynthesis, there are two separate phases or reaction: the light dependent reaction in which light energy is used to create higher energy molecules, and in this case we have a production of gaseous oxygen, O2, and we have a light independent reaction part in which carbon dioxide is transformed into organic compounds like carbohydrates using such molecular energy. So there are typically we subdivide photosynthetic activity into two steps. The first step is the so-called light dependent, in which we have the creation of high energy molecules. I call you, we call these molecules ATP, adenine triphosphate, and so on, which are the energy carriers for all the cellular processes. In this case, oxygen is produced. And then we have a light independent phase in which this energy is employed to convert or transform inorganic forms in carbon of carbon into organic compounds, such as carbohydrates. Of course, light, we say, is a limiting factor for photosynthesis. In this case, we imply the photosynthetic active radiation, we said, is 56% of the total incident radiation. For example, in water, we apply the Lambert-Beer model, for which we say that the intensity of light or intensity of radiation arriving at depth 8 is equal to a constant alpha times the incident radiation of the surface of the photosynthesis, what is reduced by 56%. So this incident radiation, even 56%, is able to perform photosynthesis. Then we have a parameter that is the light extinction coefficient gamma and the depth expressed by h. In this case, we may model, for example, the photosynthesis photosynthetic rate by employing these formulations. In this case, we may write that the photosynthetic rate is equal to a maximum photosynthetic rate that is reduced by this function, in which we describe the light adaptation parameter. So by introducing intensity of light, that is the saturation level of intensity. I recall you that we are talking about these kind of models. So we are describing the effect of saturation by introducing an IK parameter. In this case, we may model photosynthetic rate by reducing the maximum photosynthetic rate by a function linked to the characteristic of machinery that is performing photosynthesis. But we may also recognize that the photosynthetic rate also depends on temperature, as all enzymatic kinetics do, as we have seen here and there, and on pH. We may include these dependencies by employing these two types of submodels, which we may write that the photosynthetic rate as a function of the temperature is equal to a maximum rate at 20 degrees reduced by this factor. And we may rate an analogous for pH, so by writing that the photosynthetic rate as a function of pH is equal to a maximum photosynthetic rate at neutral pH that is 6.5, reduced by a quantity that is described by this model. In general, we assume that the optimum pH value for photosynthesis is around 8.5, because in this case we have an equilibrium between the dissociation of CO2 into carbonates. So this is the way we may describe the effect of lights to primary production. We have seen these models. Before going on introducing the models for algal growth, we shall have a short discussion concerning different types of algae, but I think that we shall stop the lecture of today here, and we will continue next week going into more details on how we can model primary production as a consequence of photosynthetic activity. Please note that this is really the model that is including, embedding all the ideas, the concepts that we have discussed up to here. And so this is the model, the most complete model, but will most completely include all the factors that we have described during the class. Okay, by now we stop here. If you have any questions, I'm available for your questions.
I have a question, Prof. Excuse me.